Hello, Dr. Ko. My name is Hello, Dr. Ko. My name is Shazeb Ahmed, and this is part one of exam three. Here we're going to show that the function of the form e raised to the negative alpha k squared t times e to the ikx are solutions to the uniaxial time-dependent heat diffusion equation with no heat generation. All right, so let's get started. So we have t, hope you can see, is equal to e to the negative kx times e to the negative alpha k squared t, right? So if we substitute this into the heat diffusion equation, which is dt over d lowercase t is equal to alpha d squared t over dx squared. This is our heat diffusion equation, and we then take the derivative 2 times, right? And we substitute this in. So we have negative alpha k squared e to the negative alpha k squared t times e ikx is equal to, when we take the first derivative, alpha e raised to the negative alpha k squared t times I squared k squared e multiplied times e over ikx. All right, so if we take this derivative one more time, we will get negative alpha k squared e to the negative alpha k squared t multiplied by e to the ikx. So as we can see here, this equation is equal, this equation and this equation are equal to each other. So therefore, the equation t equals e to the ikx times e to the negative alpha k squared t. So this is the expression for any value for k, and it's the solution to the partial differential equation of dt over dt equals alpha d squared t over dx squared. All right, so that's going to be it for part one of exam three, and I'll see you in the next video. Thanks for watching. Hello, Dr. Ko. My name is Shazeb Ahmed, and this is part two of exam three. Here in this video, I'm going to derive an explicit forward differencing scheme for calculating the time varying temperature profile. So let's get started. So we're going to start off with d squared t over dx squared. Hopefully I'm not getting in the way, you guys can see the picture, plus q over k, this is going to be q dot, is equal to 1 over alpha times dt over d lowercase t. So if we do q dot is equal to 0, we will get this equation. It'll be dt over d lowercase t equals alpha d squared t over dx squared, which is the unidirectional heat diffusion equation with no heat generation. So now we're going to use finite difference, and the first thing that we're going to do is we're going to break this into two derivatives. Okay, so we have, when we break this into two derivatives, we have dt over d lowercase t is equal to alpha d over dx times dt over dx. All right, so now we're going to use spatial discretization, and we're going to get tj n plus 1 minus tj n over change in time. So here j is position, and time we're going to do is n plus 1, some time plus 1. And that's going to equal to alpha, which we bring down from here. And now for d over dx, we're going to have tj plus 1 n minus tj n over change in x minus, which is the same change in x, d of x, minus tj n minus tj minus 1 n all over change x. And then we take that all over change in x. All right, so this will be our first finite difference approximation. And so if we clean this equation up a bit and we move up the change in t over a little bit, we will get tj n plus 1 is equal to tj n plus alpha multiplied by t j plus 1 n minus 2 tj n plus t j minus 1 n all multiplied by change in t. And this will be this expression right here will be all over change in x squared. Since we combine these two fractions, we have to multiply change in x, so it just becomes change in x times change in x, which is just change in x squared. And the next thing we do is clean that up a bit. So we have tj plus 1 is equal to tj n plus r. So r is just going to be our alpha dx, our alpha change in t over change in x squared. So we don't have to keep writing that. So it'll be tj n plus 1 minus 2 tj n, right, plus tj minus 1 n. And as I mentioned before, r is equal to alpha change in t all over change in x squared. And that's going to be it for part 2 of exam 3, and I'll see you in the next one. Hello, Dr. Ko. My name is Shazab Ahmed, and this is exam 3, part 2. So I'm going to be implementing part 2 of this exam in Python. I'm going to plot my results, and I'm going to show the transition from stable to unstable results at specific values of the discretization. All right, so let's get started. So first we're going to do import numpy as np, and then we're going to do from plotly.subplots import make subplots. All right, so this allows us to make subplots, and now we're just going to import plotly.io as PIO. All right. Next thing we're going to do is PIO dot templates dot default is equal to plotly underscore dark. And all right. Alright, now that we have that, our next step is we're going to be putting in the number of increments. So our size is 50 meters, so we have a 50 meter node, and we are going to do nx is equal to 50, and then I'm going to do nt is equal to 2000, which are our time increments. Alright. So the next thing that we're going to do is that we're going to do alpha is equal to 1 dot, and that's going to be our thermal diffusivity, and for a real, since it's a real material, we have to put a real number in, so that's why we do 1 dot. The next thing we're going to do is delta x is also equal to 1 dot, which is like, I don't know why I did that, which is like the size of each slice, and then we're going to do delta t is equal to 0.5. Alright, and those are our time increments in seconds. So now we're going to generate actual positions, and for this we're going to do n is equal to np dot arrange nx times delta x. So this allows us to generate actual positions. And the next thing that we're going to do is r is equal to alpha times delta t divided by delta x squared. So this is our R value, and as you remember in part 2, this is the equation to get it. So now we need to specify the initial temperature profile with the number of nodes. So we have T is equal to NP dot full NX, and we'll just say initial temperature is 20 Celsius. And now we need to like put our first temperature, which is going to be at the leftmost side, and then our temperature, which is going to be all the way to the right at the rightmost side, which is going to be our last temperature. So we're going to do T bracket 0, and we're just going to do 50 Celsius for that. And then for our final, we're going to do T bracket -1 is equal to 80, which is at the rightmost side. Alright, the next thing I'm going to do is I'm going to make a subplot with 1 row and 1 column. So for that, we're just going to do fig is equal to make underscore subplots, and we have rows is equal to 1 and columns is equal to 1. Alright, so next thing I'm going to do is create a scatter plot. So I'm just going to do fig.add underscore scatter, and parentheses our x value, which is just x, and our y value, which is the temperature. And we'll just name this initial. Alright, so this creates our scatter plot, and the next thing we're going to do is that we have to iterate this for all the time intervals. So for that, we're going to do for I in range, and we're going to do 1 nt plus 1, and that's going to iterate it for all time intervals. So now we need to isolate for the temperatures of the internal nodes, because right now we're just looking at the first and the last. We need to get the temperature of the internal nodes, and for that we're going to do something like this. So it's going to be T bracket 1 -1 is equal to T bracket 1 to -1 plus R times parentheses T bracket 2 colon minus 2 times T, and for this one it'll be bracket 1 to -1. Alright, and then we're going to do plus T bracket colon to -2. Alright, great. So this is just like the equation that we solved for in number 2 with like the minus 2j n plus 1 plus tj n plus 1. Alright, so now we're gonna do if I is 100, we don't want to plot that. Okay, so this just allows us to plot on the lines that plot the lines that are a multiple of 100, because there will be so many values and it will be really hard to see, you know, if with that many lines on the plot. So once we do that, we're gonna do fig dot add underscore scatter. We have x is equal to x. I could have just copied this down, but I'm just gonna type it out again. And we're gonna do mode is equal to lines, and for the name we're gonna do f apostrophe do I. Alright, so this just allows us to add the plots, and now we're just going to show the plots. It says that is an invalid index. Let me see. It's because I forgot to put this. X is equal to np dot arrange nx times delta x. So let me try this. Run all. X is equal to np dot arrange times delta x. It says module numpy has no attribute arrange. Don't. Alright, great. So I think I just typed an extra R there. So now we have all our plots, and now I'm going to show how it could be unstable, because delta t has to be less than 0.5, right? So if we just do like even 0.505 and I do shift enter, it's gonna probably show us some crazy graph, you know, looking like this. which just shows that it's unstable if it's a value greater than 0.5. I can also try 0.51, and yep, same result, still unstable, sorry. So this has to be 0.50. All right, that's it for this video, and I'll see you in the next one. Thanks for watching. Hello, Dr. Ko. In this video, I'm going to be doing part 4 of exam 3, and in this part, I'm going to be applying the von Neumann stability analysis to the equation we got in number 2, and we're going to show the requirement for the stability. So at the end of question 2, we had an equation of Tj n plus 1 is equal to Tj n plus r all multiplied by Tj plus 1 raised to the n minus 2 Tj n plus Tj minus 1 all raised to the n. All right. So in this equation, r, as I said in our part 2 video, r is equal to alpha change in t over change in x squared, right? So the general solution for the heat diffusion equation is dt over d lowercase t is equal to alpha d squared t dx squared. And this can actually be written as t is equal to the summation of some value k from negative infinity to infinity of some constant k times e to the I kx times e to the negative alpha k squared t, right? So for the stability analysis, we need to express the solution for one particular wave number in this equation. So we're going to actually pick t is equal to e to the I k j change in x times e to the negative alpha k squared n change in t, right? So now we're going to substitute this back into this equation, all right? And when we do that, we get Tj n plus 1 is equal to Tj n multiplied by 1 plus r multiplied by e I k change in x minus 2 plus e I k negative I k, sorry, change in x. All right. Two parentheses here, 1 plus r is multiplied by this whole expression. All right, so if we simplify that further, we get an equation of t subscript of j raised to the n plus 1. As we mentioned earlier, j is the position, and n plus 1 is some time. Okay, so once we do that, we get t jn is multiplied by 1 plus 2r cosine of k change in x minus 1. And we get cosine k change in x from the heat diffusion equation, as we talked about in one of our earlier parts. All right, so this part right here must be less than 1, or the temperature will grow to either, this part must be less than 1, or the temperature will grow to either infinity, or it'll grow to either negative infinity, okay? So what we're gonna do is subtract 1 from both sides, all right? So once we do that, we're gonna get, talking about this expression must equal to negative, less than 1, okay? Because of the cosine here. And once we subtract 1 from both sides, we get negative 1 is less than 1 plus 2r cosine k change in x minus 1. All right. And then this must be less than 1. All right. So then we subtract 1 from both sides again. We get negative 2 change in 2r times cosine k change in x delta x minus 1 is less than 0. Okay, so now we're going to divide this both sides by 2. And once we do that, we get an equation of negative 1 is less than r cosine k change in x minus 1. All right. So the smallest value that we can get here is negative 2. All right, that's the smallest value that we'll be able to get, okay? And this equation sets a constraint for r, all right? So r has to be less than 1/2, all right? So this is what sets the constraint, because if r is greater than 1/2, right, then this can't be used because we run into a lot of stability issues, which is what we're trying to avoid. All right, so in order to not run into any stability issues, and we use this equation, r has to be less than 1/2. All right, thank you so much for watching this video, and I'll see you in the next one. Hello, Dr. Ko. In this video, I'm going to be doing part 5 of exam 3. So I'm going to be deriving the Crank-Nicholson finite difference scheme for the heat diffusion equation. And I'm going to show that it has no stability constraints. So let's get started. So in the Crank-Nicholson, it takes an average of the second derivative discretization at a current time, and then also at a succeeding time, right? So it's gonna look something like this. So we have temperature at J n plus 1 is equal to temperature J n plus alpha change in T over change in X squared. So this is our R value. And then you have Tj plus 1 n minus 2Tj n plus Tj minus 1 n So now you also have to do it at a succeeding time. So at a succeeding time, it would be, instead of n, it'd be n plus 1. So we have tj plus 1, n plus 1, minus 2 tj n plus 1 plus tj minus 1 n plus 1. All right. And since we're taking an average, we divide everything by 2. All right. So minus. All right, so we take an average at the current and at the later time. All right, so this method is better because there are no constraints on change in t and change in x. So that's what we're trying to derive for here. So now we're going to move the 2 out, and we are going to get tj n plus 1 is equal to tj n plus alpha change in t all over 2 delta x squared. And in this, we're just going to have this numerator here. So we have tj plus 1 and minus 2 tj n plus tj minus 1 n plus tj plus 1 n plus 1 minus 2 tj n plus 1 minus tj minus 1 n plus 1. All right, so this will be our new R value. And now we're gonna continue on with the stability analysis. So the first thing that we're gonna do is we're gonna move the R. So we're gonna have, on the left-hand side, we're gonna have negative R tj plus 1 n plus 1 plus, in parentheses, 1 plus 2r, and then we multiply that by tj n plus 1 minus r tj minus 1 n plus 1. All right. And on the right hand side, we're going to have r tj plus 1 n plus 1 multiplied by 1 minus 2r tjn plus r tj minus 1 n. All right. So now we're going to isolate a factor from this equation. So let's factor out the node at position J. And when we do that, we get something like this. So we have tj n plus 1. This will be negative r. And now we're gonna use our heat diffusion equation and sub in some values. So we have E ik change in x plus 1 plus 2r minus re negative ik change in x. All right, so that's going to be on the left hand side, and on the right hand side it's going to be tj reik change in x plus 1 minus 2r plus reik change in x. All right. So now we're gonna clean this up. All right, so I'm just gonna move this value over. So I'm just gonna be dividing. So I'm gonna have tj n plus 1 is equal to tjn, forgot the n right here, need this value all over this. So we're gonna have 2r cosine k change in x plus 1 minus 2r. Alright, and we're gonna divide that all by 1 plus 2r minus 2r cosine k change in x. So now we need to show that this expression has values forming for different values for r. All right. In order for it to be unstable, we need to find out, are there any values for this expression for r where it equals greater to 1? If that is the case, we're going to end up with an unstable finite differencing. All right. So now we factor, and we get, and factor this out, make it look nicer. So we have tj n plus 1 is equal to tjn. This is going to go to 1 minus 2r multiplied by 1 minus cosine k change in x over 1 plus 2r 1 minus cosine k change in x. All right, so we're almost there. So we know that this value, 1 minus cosine k change in x, is always going to be positive, right? So we can think of it like this if it's always positive. We can think of it as tj n plus 1 is equal to tjn all multiplied by 1 minus 2r multiplied by y, some positive value greater than 0. And same thing on the bottom. We can do 1 plus 2r y. And I'll write this out again. And y will be greater than 0. All right. So if y is greater than 0, first of all, we have r is equal to alpha change in t over 2 delta x squared. And we know that this value will also be greater than 0. All right. So it's guaranteed that it'll always be less than 1, right? So we can write it out like this. So this value, 1 minus z over 1 plus z, right, will always be less than 1. So that's guaranteed for us. So this shows that the Crank-Nicolson method is stable no matter what values we have for delta t and delta x. And that's why the Crank-Nicolson method is the best method, because there are no constraints. All right, thank you for watching, and I'll see you in the next one. Hello, Dr. Ko. My name is Shazeb Ahmed, and this is going to be part 6 of Home Exam 3. And in this video, I'm going to be implementing the Crank-Nicolson method and also plotting the temperature profile as a function of time. All right, so let's get started. So up here we have everything same as before, but we added the Skype.lin ALG import solve banded. So what this basically allows us to do is solve the
linear algebraic equations with a banded structure, because that's what we're going to have in the Crank-Nicolson. So the first thing that we're going to do is nx is equal to 100 and nt is equal to 2000. And the nx is the number of spatial divisions, which is also the number of nodes, and nt is the number of time steps that we want the function to take. So now we're going to add some parameters. We have alpha is equal to 1 dot, and that's the thermal diffusivity. I keep having trouble. Diffusivity of the material, and the next thing is delta x, which is our spatial increment, and we're going to do 0.5 for that. And the next thing is delta t is equal to 0.5, and that's going to be our time increment. So next we're going to input the equations to solve for x and r. So x is going to equal to np dot our range nx, and we're going to multiply that by delta x. So this basically generates a list of spatial positions for the plotting. And now we're going to add the equation for the r value, and remember r is equal to alpha times delta t and divided by delta x, and delta x is squared, and we divide that by 2. So here we're just defining r for Crank-Nicolson, and we have to keep in mind that when we divide by 2 in the denominator, that's for averaging. So that's like the main concept of Crank-Nicolson. So done for that. So the next thing I'm going to be doing is I'm going to be inputting the matrix of the diagonals. So we'll just do array is equal to np dot zeros 3 comma n x minus 2. All right. So the 3 is for like the number of rows. So there's going to be a row for the upper, there's going to be a row for the main, and there's also going to be a row for the lower. These are all diagonals, upper, main, and lower diagonal. And the nx minus 2 columns, because we have that there because temperatures at the left and also the right ends are set from the beginning. So now I'm going to be inputting the array for the upper diagonal. So that's going to be a brackets 0 comma 1 and colon is equal to negative r. That's our upper diagonal. And for our main diagonal, we have a brackets 1 colon brackets 1 colon is equal to 1 plus 2 dot times r. All right, that's our main diagonal, and the next thing that we're going to do is our lower diagonal. So we have a, again, brackets 2 colon, but this time it's going to be to negative 1 for our lower diagonal, and that's also going to be for negative r. All right. So the next thing that I'm going to do is I'm going to be allocating the vector of RHS of the set of the linear equations. So to do that, we're just going to do we'll just do b for that. B equals np dot zeros nx minus 2. All right, great. Now we have that. The next thing I'm going to do is b equals to r times t, and I'm going to type this out first, and then I'll explain what I'm doing here. And it's going to be plus 1 minus 2 dot times r times 2 dot r times t brackets 1 colon negative 1 plus r times t of brackets colon of negative 2. So this basically fills in the values for b. All right. So the next thing that we're going to do is we're going to add on the terms for the first element, because this b equals r times this current line I'm on is just for, you know, the nodes inside for that b value. We also want to add the terms on for the first and also the last element. So for the first element, we can just do b brackets 0 is equal to b bracket 0 plus r times t bracket negative 1. So this adds on the terms for our first element, and now I'm going to add on the terms for our last element. And for that, we'll do b brackets negative 1 is equal to b brackets negative 1 plus r times t brackets negative 1 instead of 0. All right, so now I'm going to do fig 2, and this is going to like add the plots, and I'm going to do like make subplots, rows and columns with one row and also with one column. So I'm just going to do fig is equal to make underscore fig is equal to make underscore subplots and rows is equal to 1, columns is equal to 1. All right. And now we're gonna give it a name and the x and y values. So I'm gonna do fig again, fig dot add underscore scatter. X is just equal to x. The y will be our temperature, and we'll give it a name of, let's just put initial for now. All right, so the next thing we're going to do is we're going to create a range like we did in part 3. So it's just going to be for I in range of nt plus 1. All right, and the next thing we're going to do is we're going to do t bracket 1 colon negative 1 equal to solve for the x value and temperature for the y value, name solve banded of 1, 1, A, B. Alright, so now I'm gonna solve, input the equation that we used to solve for B, and it'll just be the same equation up here, so I don't have to type it again. So B equals, alright, and then we're gonna also put in our first element and last element for the B0 and B negative 1, the terms for the first element and also terms for the last element. So they're up here. Do B for that, and just like in part 3, if So if since we don't want so many, lines in the plot, we're gonna do if equal to 0. So this basically just allows us to plot for every 100th term. So if it's a multiple for 100, we'll have a line for that. And now we're just going to do fig dot add scatter. We have x is equal to x, y is equal to t, and for the name we're gonna do f, we'll do I times delta t, and we'll have s here. S. Alright, great. Not to add a colon there. B equals, let's see where my mistake is. B is equal to R times T, 2 colon plus 1 minus 2 dot times R times T 1 to negative 1 plus R times T colon negative 2. I'm going to run all, see if that fixes it, because sometimes that happens. It says T is not defined. Pretty sure T is defined. Oh, I forgot to define T earlier. Add a code. Alright, so define T, we have T equals NP dot full, and we're gonna set the initial temperature value, and we'll just do 20 Celsius, and we'll do T of 0 is just 50 dot, which is the left side temperature. It starts at 50 and it stays at 50, and then I'm gonna do the right side temperature. T negative 1, and we'll just do 80 for that. Run all. Let's see where my mistake is, because this does not look right at all. And give me one quick. Alright, so I figured out what my mistake was. I forgot to add a comma right here and a comma right here, so I just took it as that full array. So here we have our final plot, and yeah, that's it for this video, and thank you for watching.